Live stream to take. All right, it looks like we're streaming now. Again, if you came in a bit late there, apologies for screwing up the solutions on you. I wasn't meaning to, just something happened, not sure what. Let me hit pause over here before we get going. All right, there we go. So what are we going to do today? We'll finish up talking about power from chapter 7, which is on page 8 in workbook volume 2. And then we're going to go on into chapter 8 and just start muscling through chapter 8. And then on Wednesday, you'll have your chapter 6 quiz. So, all right, there's that. If we have questions, we could talk in office hours. That said, let's go ahead and get rocking. All right, so last time, briefly, we'll just start with some whiteboard work here. Again, page 8 in the workbook if you want it. But so we're going to use this symbol P for power, just some kind of bubbly P to distinguish it from pressure, from density, and from momentum. These are all different P's that we use in physics. So that's momentum. That's chapter 9. This is density. Rho, your density. This is pressure. We'll do that in chapter 14. And then this is power. Now, if you recall, the units of power are watts or joules per second. So we say this is essentially dE dt, the time rate of change of energy. It's approximately equal to delta E over delta T. So a change in energy over change in time. So if the units help, it's joules per second. Okay, so this is a joule. Let's just write that out. So energy over time. That's our definition. And all right. And let's go ahead and get into the screen share of the workbook here. See if there's anything else I want to say about that. So I think we said page 8. Sorry, I'm scrolling. I should have just skipped to it. There we go. Whoops. Let's go back a couple. Oh, interesting. I wonder if I labeled this one from the beginning. Whatever. Doesn't really matter. All right. So, so there's a couple of other tricks here that we see. If you're trying to get the average power, we just use the deltas. If you needed the power at one given second, you could use the derivative. And notice it could be shown you can also get the instantaneous power if you know force and velocity. So you could figure out the force dotted with the velocity. And so notice again, that trims off the component parallel. Dot products trim off a parallel component. So you'd either get the velocity parallel to the force, or thinking of it another way, you could say the force that is parallel to the velocity and get the power with that. All right, so if we start with this one, let's just start with 7.9. We'll try and do 7.9 and 7.10 together very briefly and then move on to chapter 8. So give me a second here, move something. And you got the solutions to this, so if I'm too slow for you, follow along with the solutions instead. Otherwise, I'm just going to try and get this drawn. We're going to go some distance h in time t. Okay. And this has some mass m. All right. All right, so part A says acceleration. So let's go ahead and do this one. I'm going to move this book over here so I have it in front of me. So you've got the question now. Let's not overthink this. A lot of this is review. So first it says get the acceleration. If I ask a question about acceleration, what technique do you think you might do?
Draw an FBD.
Okay, if we do an FBD, we get some forces. All right, so what would be the forces on it? What's one of them?
Gravity pointing downwards.
mg. What's the force upwards?
Tension.
Okay. And then which way is this particular one accelerating? Do we know? I think it says it accelerates upwards in this problem. So we know it's accelerating upwards, but we don't know that value of A. Do we know the value of tension?
I don't think we do.
So that was a good guess. That's exactly what I would have done as well. I'm like, the problem's asking for acceleration. I would have tried forces. That didn't work. What else could we try? Good thought. Didn't work out.
Kinematics.
Exactly. Kinematics might involve these two knowns. We might be good to go. All right, so let's try that. And I'll just leave this sitting here. So in this case, delta y is equal to v initial y times time plus 1/2 a sub y t squared. Sorry, I'm squeezing that in there. Let me scoot this a little closer in case it's blurry. And again, I should write down the problem number. Bad form here. This is 7.9. Sorry about that. 7.9. Okay, well, it's what's the initial y? Do we know that?
0.
Yeah, it said from rest, so this is looking good. So now in this case, delta y is positive h because we're going up h. We have 1/2 a sub y t squared. H is known, t is known. We got a y. Flip that around, you could probably beat me to it. But I think it's going to be 2h over t squared. So that I don't screw up later on, what should I check right away?
Units.
Yep, meters per second squared looks good. This wouldn't help us with missing the factor of 2, but we're feeling pretty good. Nothing too crazy there. Let me do something really quick here. Okay, just to get a little glare out of there. All right, so now, great, that's part A. Part B said, find the final speed in terms of h and t. So what would you try next? Could we do energy to find the final speed? What do you think? Or sorry, a work problem. Or what are you doing on your paper?
Would we use another kinematics?
Yeah, kinematics would probably be the easiest. If you tried to do this with work and energy, you might be able to do it because you'd have the acceleration, but first you'd have to figure out the forces and it would be long. So to me, like kinematics is the way to go here. So we see that every once in a while, kinematics comes in handy in later chapters. So this is part of the reason I was so ruthless about trying to drive this stuff into your brain. All right, v initial y is 0 again. And so here, v final y, we know ay, that's just 2h over t squared times time. And notice it's not just distance over time. Do you see that? It's not just h divided by t. Even though h over t has the right units, it's actually 2h over t. So this is actually pretty typical. The average velocity would be h over t. The average velocity occurs halfway up. So we would be off by a huge amount, by 100%, if we ignored that factor of 2 there, or 50%, depending how you want to think about it. But yeah, all right. So there's the speed at the end. Part C, determine tension in the cable. So how would you go about doing that? Tension in the cable.
Now you use FBD.
Yep, we got the FBD. We know mg. We've got A. We could solve for T. All right. So in this case, is it going to be T minus mg, or is it going to be mg minus T that is equal to ma?
T minus M.
Yeah, because in this case, we want these two to have the same sign. The tricky one that everybody screws up is when it's accelerating downwards. Okay, so C out of this, let me just scoot down a little bit more. We see that T minus mg equals may. And then from there, we could plug in all this stuff. And so the tension is equal to, let's see, it's going to be mg. I should be careful. This doesn't equal that, right? We could rearrange it to solve for T. Okay, it's mg plus m, and I don't want to screw this up, times 2h over T squared. Obviously, we could rearrange this a bit and make it look prettier, but for now, that's good enough. Okay, so we see that we could do a little bit of kinematics and forces to learn all kinds of certain things about this. Great. Next, determine the average power. So this is the new part. If we're trying to figure out the average power, let's try and use the definition of average power. Change in energy over change in time. So I'm going to kind of clean this up a little bit so I have some room to work. I'm going to write down our key results here. All right. So one of the results, we found our acceleration in the y direction was equal to 2h over t squared. We know that our final velocity was 2h over t. And we found that the tension in this problem was some big mess. Let me write that up here. Just organizing, okay? I think we found that the tension was m times the quantity g plus, just kind of color coding it here, 2h over t squared. So that was all the results that we found. Let me get that just a little bit more on the page there. Sorry about that. In part D, we were up to part D. It says average power. All right. So in this case, that definition is change in energy over change in time, right? And so in this case, and this is the average power delivered by the motor, right? All right. So in this case, we could say that will be the change in the kinetic energy over the change in time, which is 1/2 mv final squared minus 1/2 mv initial squared. If you've forgotten, the definition of kinetic energy was 1/2 mass times speed squared. So this was just how that was defined. This also has units of joules. So the change in kinetic energy from this numerator would just be that. The time interval here, the change in time, happens to just be t. We know the initial speed is 0 from the problem statement. So now we could plug all this in, but wait, we know what V final is, right? V final was this mess up here, 2h over t. So just plugging that in. It looks a little sloppy. Let me clean that up. Then we've got the t from the bottom. So out of all this, we could simplify this. Power average exerted by the motor, right? The motor is basically causing this thing to speed up. Gravity is doing something else. We'll worry about that later. But so we have 1/2, let's see. There's going to be a 2 pop out. So what do we get? I think we get 2mh squared all over t cubed. Let me see if I screwed that up. So again, we get a 4 over 2. That's the 2. There's only one m. There should be h squared up here, and there should be t squared, and then we divide by another t. So I think that's right, t cubed. So in this case, we could try and check the units, but it's a little bit tricky, right? And so here, this, right? So, well, let's go ahead and do this. We know that a watt is equal to a joule per second, but a joule is like a Newton meter. But what was a Newton? Does anybody remember what a Newton is?
Kilogram times
per
meter.
meters.
Yeah, a kilogram meter per second squared. So now, just so I have room for the unit check, I got to lower this down again. So this is a kilogram times a meter per second squared times a meter divided by a second. And so, whoops, that's sloppy. Notice we should get kilograms on top, meters squared on top, seconds cubed on bottom. So the units look good. All right. Questions on that? All right. Now in here, I should be careful, right? We could debate whether or not this is the total energy, and we're going to describe that more in the next chapter, because you could say, well, wait, doesn't the tension have to exert more force than this value to overcome gravity, right? So so for right now, I'm mainly interested in checking the units. We could talk about the idiosyncrasies of that later, or look at the solutions and see if there's anything I want to say at the end. But for right now, this just shows you one way to do this one. All right. So yeah, that's average power. Essentially, you could do a change in energy over a change in time. Now, I guess maybe what I'll do is I'll do that the other way right now. So unless there's any questions, I'd like to show you another style for this right now. So this would give you one estimate. Here's another style. So we could say that the power average is equal to work over time. Now you might be saying, well, wait, isn't work the change in kinetic energy? You're absolutely right. So what if we want to get the work done just by one force? What we did in the last one was the net work. Okay, so in this case, we could also do just the work done by a single force. Well, that would be, we could get the work done by tension over time. So the work done by tension would be tension times the distance times cosine of the angle between. We could draw a picture. Tension is upwards. And actually, in this case, displacement is also upwards, right? We're going upwards, distance h. And so what is the angle between these two vectors?
Zero.
0. So in this case, our angle would be 0 degrees. So you could actually get the work done this way. T times H. Now notice in this case, we have a value for tension. We could multiply this by H, and I think you'll find something interesting here in the result. So when I do this one, we see we get M times G plus 2H over T squared. That's the tension times H. Okay, so this would be the work done by tension. All right, and so in this particular case, the tension is caused by the motor. So you could say, well, shouldn't we be getting this work? And I could say, yeah, I'm fine with that. So depending on how you word the problem, and we could go read the solution and see if there's anything else I want to say here. But in this case, notice we get a slightly different formula. We get mg plus 2mh squared over, and this would be mg over t plus t cubed. I'm just kind of rearranging this a little bit. So remember, the power is work divided by t. So if I take this term and divide it by t, plus this term and divide it by t. So depending on what's going on in this problem, how far you move it, what the time interval is, etc., this term you could argue might be negligible or maybe not, but yeah. So if we were trying to get the power average associated with the tension force, it's actually a little bit larger than that previous result we found, because this one, you're accounting for the fact that the tension also has to oppose the weight of the elevator itself, plus make it speed upwards. So let's go look at the solution, see if there's anything else I wanted to say in there. And you could unmute at any time and ask questions here. Whoops. Let me just do this. Control F. What problem was this? 7.9. Yeah. And so, all right. So it looks like I wanted you to actually account for the work done by the tension. So there we go. So that seems reasonable to me. So that first answer was approximate because it ignores this part. And that could be non-negligible. Again, it depends on the time and things and the heights, etc. All right. But yeah, it's obviously greater than mgh times t. And that's something important, right? Because clearly we have to have the motor outperforming the work done by gravity. Otherwise, it's not going to go upwards. All right. And then since we're here, let's go ahead and do part E. Part E is where we can use that cool trick. If I want the instantaneous power, I take the tension vector and dot it with the final velocity vector. Since they're both going the same way, I just take the tension and multiply by the final speed, and notice you get a slightly different answer. And in fact, we see that this is a typical result for constant acceleration stages. You typically have twice the power output at the end as at the average point in the middle. All right. So sort of like we have final speed was twice as big as the average speed. All right. I'm going to pause for a second. Any questions about this? That's 7.9. All right. That's cool. Nothing too crazy there. All right. So, and then maybe right now, let's go on to 7.10 just to briefly discuss it. All right. So I'm going to go back to 7.10. So that was pretty much that problem. That was just kind of getting you used to the units and some of the idiosyncrasies associated with these types of problems. All right. So turns out this problem at first looks ridiculous. You're like, particle, you give me some random function. This seems really, really silly. It seems totally made up and like your physics teacher is just torturing you. And it turns out now that we're doing labs where you use video capture, maybe you can kind of get a feeling for why this problem is actually cool and perhaps even useful. That's scary to say. The idea is this. Imagine you take a video of anything in the world, all right? It could be a frog. It could be, an elevator. It could be a car. It could be all kinds of things. And you use video capture to track the motion of the object. And what you do is you take that data, dump it into some spreadsheet program, and get a trend line. And you could make the trend line as crazy as you have to accurately model the data. So you find some trend line. Basically, you would figure out an equation like this using data from a video. once you do that, look at this. You could follow this procedure and figure out the net force on the particle. You could figure out the average or instantaneous power. And so we could actually use this technique to figure out the power output of various objects in real life. And so I just want to point out that is why I think this problem is actually a lot more useful than it initially looks. Because with some standard lab techniques, you could get weird functions like this for weird particles and figure out their power outputs. So I'm going to pause there and see if there's any questions. All right. Now, the process here is very similar. In the last problem, I don't know if you remember, we found the acceleration and the speed, and then we use that to find the force. Well, look what we're doing here. Find the speed and the acceleration, technically velocity and acceleration vectors as a function of time, because this is 1D motion. Positive would imply a positive number, negative would imply negative I hat, that kind of thing. So then we get the force, right? You could multiply mass times acceleration. That should get you the net force. So that's, again, a lot like that first model we did where I ignored the... anyways. And then we could do this type of trick. If you want instantaneous power, you'll have an equation for force as a function of time and velocity as a function of time, and you can literally just multiply them together, and you've got instantaneous power. And if you want the average power, how would you get average power? Remind me.
Change in energy over change in time.
Exactly. And change in energy has to do with the velocity at any one point. So there you just plug in certain values. You'd plug in 0 and 2 into that velocity equation. You could get the change in kinetic energy, and you'd get your change in, you'd get the average power output from that. So I'm going to leave this one for you to do, just to kind of walk you through it. It's very similar to what we just did, except instead of being constants for V final and for A and for tension, they're actually functions of time. Similar work. All right, any questions about that? All right. I thought this was a fun question too, by the way. So if you get stuck on this one, you might have trouble with this one at first, but the idea is, here's a problem where air resistance is non-negligible. But the trick here is, if you can learn something about a car on flat ground with speed V, right, you could actually figure out the change in power output required when you have to go uphill, or if the wind picks up, or all kinds of things. So I'll let you look at that one later. And I think we already discussed this one and how irritating this is that I forgot the italics. But again, here's another one that really throws people for a loop. 7.12 has got a lot of what I would call decoy information, right? If we're talking about the entire 10 seconds of motion here, all you need to do is say, well, the initial energy is 0. The final energy is 1/2 times the mass times the final velocity squared, and then divide by 10 seconds, and you got yourself an answer. And who cares about these different stages? The whole thing that's interesting about average power is it's ignoring the stages. It's just comparing initial to final. So definitely read the solutions on 710 through 712 so you don't get lost. If you make sure you check your work carefully, because you might be surprised and miss some subtle things. And that's chapter 7. This is a good review problem. Notice you got to make a bunch of sketches. So I know it may seem silly, but I believe by sketching things, you're forced to understand it better, because you're not just getting one specific value. You're trying to understand how these things change over time. And so that is a good review of everything we've done till now. So this is a really good problem, I think, to review. And this one requires separation of variables, so I'm not going to ask you to do that one. All right, pause for a second. It looks like I do want to talk about force distance trade-offs before we go into the next chapter. So that's a classic physics topic. Any questions? Let me go to gallery. All right.
I have a question.
Yeah, go for it.
Why would you want average power instead of instantaneous power?
Well, a lot of times it's easier to calculate average power from real life scenarios. So let's say you don't do video capture, right? Let's say you're driving your car and you go from 0 to 60 and you just time it. Well, it's really easy to say I went from 0 to 60 in 12 seconds. So I know 60 miles an hour is the final speed. It's much easier to calculate average. Now, that said, if you know the instantaneous power, you could always get the average later in many different ways, or at least a couple. So it's better to get instantaneous, but it's usually far easier to calculate average power. Is that good?
Sounds good.
And then in a real life situation, when you're doing video capture, you're not really getting the instantaneous power. You're just getting the average power over a tiny time interval. And so in practice, even, you could cut up the time interval so short that the average power is approximately equal to the instantaneous power, but you're always usually doing some kind of average. Is that making some sense as well?
Yeah, it makes perfect sense.
Yeah. So, yeah, it's very rare that we get a perfect number for the instantaneous power. It's usually approximated by the average. All right, at least in a lab setting. Good question. And go ahead and if I'm going too fast here, interrupt me. All right, so I'm going to go ahead and plow on into this. So let's just consider this. You have a block and you're going to raise it up here and lift it, and you're going to try and notice I'm going to assume the box is lifted at constant speed. So strictly speaking, we know it's going to start at rest and you're going to accelerate it upwards and then bring it back to rest. So, but if we move this box very slowly, the acceleration phases are pretty negligible. And so we're going to ignore that and just talk about this thing moving at constant speed, raising it up and putting it up here. So the work done by this case should equal F1 times the height. If acceleration is negligible, so if A is approximately equal to 0, how does F1 compare to mg?
They're about the same.
Yeah. So notice, and the angle between them, I should be careful here. There's always a cosine of an angle, but in this case, the angle is 0 degrees. So cosine of 0 degrees is going to go to 1 because you're lifting this thing straight up. The force is straight up. The angle between is 0. So that's great. So notice the work in lifting this thing up is mgh. This fits our kind of MGD idea that, we usually get a lot of MGDs when we're doing work in physics. Okay. So now, what about this case where it's at an angle? We could split this thing into components. We could do an FBD and do all the work on this one. Now, I hope you agree it's going to take less effort to push the box at constant speed. This normal force is canceling out a lot of this force. And then obviously there's a small increase from this component. But the idea here is if you use a very small angle here, we expect it should be a little bit easier to push this box up the ramp, even though we're not pushing it at the right angle. In this case, you could go through the calculations, figure out all these things, and the work, and you could read this in the solution, should end up being exactly the same to raise it up. Crazy. So the work done by force 2 should exactly equal the work done by force 1. Now, here is the deal. All right, so in this case, just because the work is the same doesn't mean there aren't subtle differences. The force in 2, we expect that the force in problem 2 is less than the force in problem 1 because this angle is so small. However, look at the distance covered. The distance is larger. And so the product of force parallel times distance is actually the same. And this is why we use ramps, right? You're pushing on objects. You need less force, but you do the same amount of work because you push over a larger distance. So that's called a force distance trade-off. And this is what levers do. This is what simple machines do. Before I scroll down on the page, I'm going to see if there's any questions here. We should get the same work, even though we used a smaller force, but you had to push it over a larger distance.
So is work technically just related to displacement?
Yes, and remember, so strictly speaking, the definition of work, if I could write that up, I'll write the most general one I can find here. It's equal to the integral of force vector dot displacement vector, which is approximately equal to, for constant force, it's just F is equal to dot displacement. I'll call it delta R for right now or whatever. You could call it delta X, you could call it delta S, that doesn't really matter. So again, it's the force vector dotted with the displacement vector. And then that's where this cosine comes from. The cosine comes from this dot product. And basically, you could group the F and the cosine together, and that's where I get force parallel. Think about it. If there's a force this way, the force parallel, hopefully you could agree, the force parallel would be F2 cosine theta, right? And so this force parallel, that's essentially from the dot product. Is that good, Esteban?
Yeah.
Yeah, sorry. That's a little sloppy there. That should be F2 parallel. All right.
So thinking about it in energy consumption, you use up the same energy. It's just you just need less force to move the object.
Yeah. Well, in this case, we're going to talk about energy in the next chapter. So let me say it this way. The change in energy of the block is the same for each of these two scenarios. Now, in this case, I think you actually spend more energy in terms of calories inside your body in version 2. Because look at this. You're having to push, and some of the force is not helping you, right? So there's a weird difference between energy you spend and change of energy in the object. Because this force is not perfectly aligned with the displacement, we're actually going to be wasting some Snickers bar that we ate for breakfast, right? Some of the energy, some of the food energy in your body is being wasted by having to push and cause your muscles to tighten in a direction that's not helping the displacement. But you do get the same change in the object. Here's the deal. Sometimes, right, there's an issue with the human body. Sometimes the human body can't exert that large of a force, even though it would be more efficient. So just because this would use less energy doesn't mean your body can do it. This might break your back. And so even though we're wasting some energy, you aren't laid out in the hospital for weeks by using a ramp. So we might spend a little bit more, but it's actually more sustainable. Does that make that subtle distinction clear, Esteban, or does that make it worse?
Yeah, no, that's makes it really clear. So my question now is there always wasted energy in pulleys and levers?
In any real system, absolutely. Because there's friction in any real system as well. So now think about this. When you're just lifting this straight up, I hope you agree that air resistance is probably completely negligible. Whereas on a real ramp, there's probably going to be some friction. And even if you had wheels to lower that friction, the axles have a little bit of friction. And what if you put this thing on a dolly, right? That would help. But, right, so yeah, there's always real life issues with real life pulleys. And let me see if I have one for you here. Hold on. Let me find it. I got a lot of different links up. Let me see if I can find this. Is it this one? Hold on. Let me see if I have my oh shoot. I've got so many. There we go. I'm trying to get these organized, but you just made me think about, oh shoot, that's the wrong one. Let's go to, is it this one? Gosh, so many videos. It's starting to get hard. I've got like 250 videos. So, and well, no, actually I've got probably 1,000 or more by now. So it's getting kind of confusing. I'm working on my organization. Let me go to, I think it's this one. This will get better later, but sorry, it's not perfect right now. Block and tackle. Here's one. So I'm going to mute this so I don't have to listen to myself. But the idea is, in this case, let me make that full screen here. So I'll just speak about it live. And let me pause here. So the idea here, if Angus probably, let me just let this play for a second. He's going to come in here and we'll get a better view of this. There we go. So the idea now, you could see that this rope is coming up and it goes around this pulley. Then it goes around this pulley and it hooks to the bottom of this mount. So here's an actual pulley system. And now here you could actually see exactly the same kind of issue I was just talking about. I'm pulling at an angle here. So you could debate whether or not that angle matters. I could try to pull perfectly straight down and we could debate whether this matters or not. But the idea here in this one, if I fast forward to the numbers, if I remember right, this has 11 pounds approximately of force. Sorry, the scales were in pounds, not newtons. And then up here, I ended up with, I think it was 18 pounds. Now I want you to think about this and where this comes from. Okay. I lifted this situation at very slow speeds. And so the acceleration stages were pretty negligible. And I tried to lift it perfectly smoothly. I wasn't perfect, but ideally you have two ropes here. So here's a picture of the bottom pulley. You've got 11 pounds down. How much should each side of the string be pulling up? Approximately.
5.5 pounds.
Exactly. Now I can actually tell, so I'm going to stop labeling the units. Sorry about that. So now I don't know if you could tell, look at the top pulley. There's a support going up that's 18 pounds. And then notice there's a string here, and a string coming down this way, and they're all pulling down. Now remember, it's actually all the same string. It's 1, 2, 3 segments of the same string. So how many pounds are in each segment there, if you had to guess?
I would say 5, 5, and then the rest. So it would be 7.
And okay, so it turns out there's probably some spread here, but approximately it's 6, 6, and 6. Now, yeah, so you're right that these are not all going to be exactly 6, right? But so the idea here is there's going to be a little bit of friction each time you go around. And we see effectively there's 1.5 pounds of extra friction in the system somewhere between this spot, right? Somewhere between that spot and my hand, there's about 1.5 pounds. So you could argue if it's the same in each section, probably not. But there's kind of an estimate for you of a real system. Is that good enough?
Yeah, no, it's plenty more than that. I just find it really interesting because I always thought like pulleys and levers caused you to use less energy, but it seems like you're always going to use more energy. It's just more convenient or less force needed initially.
Yeah. So the idea is, think about this. If you want to lift an engine out of your car, that's going to be way too heavy. Now, you're not getting something for free. If we watch this video here, let me skip forwards a bit. Okay, so let's see if I can get this. All right. Oh, whoops, right about here. Okay, so I'm just going to play this now. So I put scales in there and I did all these measurements. And now I don't know if you could see, I'm lifting that heavy mass up, and notice the issue here. I'm going to point out, I know the camera's not steady and I've got zoom blocking me. So give me just a second here. This is approximately how far I pulled the string. And notice the mass only moved up about that far, half the distance. So the idea is I pull with half the force. So I used half of the weight, but my distance was twice as far. So I'll call that 2h. And this distance over here. And so the idea is you're not getting something for free. You're cutting the force in half, but having to work twice as over twice as much distance. And then on top of that, you have to pay the frictional costs. So, but this makes some objects feasible to lift that you otherwise could not lift. All right, I'll shut up for a sec. Esteban, was that good?
Yeah, no, it's plenty good.
All right.
Very interesting.
It is. And these are called force distance trade-offs. Enough on that. Let me escape out of here. Let me just get out of this and reorganize my windows here. Hold on a sec. Got to escape out of this one. Whoops, I got to stop this video. There we go. Did I pause it? Yes, I did. Sorry, too much windows. I need to get back to this. There we go. And back to this. Sorry. All right. All right. So you could go through these problems if you care, but if you're also interested, if you're a mechanical engineer, this is kind of your cup of tea, right? So you could read about the simple machines, the screw, the lever, the wheel, the wedge, inclined plane. And this is the one I used as my example, and the pulley. And obviously you could make complicated machines or compound machines from these. And you could try, if you wanted to try and envision how you could use a screw to lift this, right? You could spin a screw and have it slowly raise the object or something. And we kind of talked about the pulley problem there. So that was actually one I was going to do anyway. So now we've done that. And then here are some really crazy ones too. If you want, you could try and figure out these. And here's where I kind of, if you wanted to understand more about the energy used by your body versus the energy used to lift things is not exactly the same. That's discussed. We already talked about this. This is a really cool one if you care, but for a mechanical engineer, you might know about this trick already. So let me just tell you about this on the board. It's easier. I've never had to use this one, fortunately. But if you're ever driving out in the woods and you get stuck in the mud or something, and your car is stuck and you can't get it out, there's no possible way you could pull out your car with a rope. However, if you have a rope and there's let's say here's the road. This isn't going to be perfect. And let's say there's a big mud patch here and your car gets stuck in the road. And there's maybe a tree right here. You could put this tree, you could wrap your rope around this tree, tie it to the frame of your car, not the bumper, so you don't just rip the bumper off. And the idea is you could actually push sideways on the rope. And let me just get this road out of here. So let's just say you're there. If you push sideways on the rope, think about this. What does this do? If you push sideways on the rope, it's eventually going to angle the rope. The rope in real life is going to stretch. So this is not a simple problem. But if we idealize it where you have a cable with negligible stretch, hopefully that's true, you could see that you're going to push a small distance this way, but the amount of force you pull here gets dramatically multiplied on the other component, right? By adding a small component of tension perpendicular to the string, you add a massive component of tension parallel to the string. And so by pushing sideways on the rope, you could pull your car out of the mud. Now you don't get something for free. You push this way for like 3 feet, then the rope becomes loose. You got to untie it, retie it again, get it super tight, and then push again. So every time you move your car a few inches, you might have to retie the rope, but that might be better than sitting there for days hoping someone magically shows up when no one's coming to save you. So that's an application of this that I find interesting. So anyways, yeah, I'll leave it at that. And so these questions I believe are not required, but if you're a mechanical engineer and you're into that, that's the application I was thinking of. And here's another weird one. If you want, so 17 and 18 are not required, but if you want to, if you're a mechanical engineer, excuse me, if you're a mechanical engineer, you might actually skim through those and just kind of read a little bit about it. Yeah, so I think that's a pretty good spot to stop. And again, you can follow the solutions, and I think we're up to chapter 8. And then since I'm thinking about it, I think what we should do now is take our break, and I'll stop the live stream and then restart it when we start up again. That way I've got them more organized in the live stream on the playlist. So unless there's other questions about chapter 7, we're going to blast on to chapter 8 next. Any questions? And you could ask them later too, and we've got office hours right after. All right, so yeah, I'm going to stop the live stream there, and we'll start it up in, let's just say,